All right. Good morning, everyone. Hope you guys are doing well. A couple of AP exam reminders I want to make sure you're aware of. So I included in the meeting chat a couple of reminders there. So first is, again, 36 Pro is not on the approved calculator list for the May 4th exam. So if you're coming in with only that calculator, then you're taking a risk, not potentially not being able to use that calculator if the proctors don't let you, or your proctors ask you to put it away. So a couple things that you can do is try to purchase one before now in the exam. You can go to Media Center to see if maybe they have one that that you can borrow or that they will loan out. Maybe some classmates who are not taking AP Calculus this year, either pre-calculus or someone who is taking stats but not AP Calculus, maybe you're able to borrow, or any students who are taking the digital exam in June won't need it on that day, so you could potentially borrow from a student who is taking a digital exam in June. So yeah, just kind of keep reminding you of the potential issue with that 36 Pro. I know many of you guys use it, but there's a possibility you may not be able to on the exam. Okay, second is this is a note from Miss White. All of you are registered to take the AP Calculus exam. You guys all signed up for it, but the default is that May 4th exam. So I think you guys should all be taking that May 4th exam. However, if you email her and you're convinced that you want to take that June exam, that digital exam in June, then please email her as soon as possible because she needs to make that change manually so that you can be in the system for taking it. And then once that change is made, you should be able to go into your College Board account and just confirm in the settings that you are locked in to take whichever exam that you want to take, either the May 4th one or the June 9th one. Yeah, again, I personally feel that I'm kind of gearing us towards that May 4th exam. So I feel like we'll be ready for us to take that May 4th exam with the pre-AP test that we're doing, with all the review that we're doing. And I just feel like, that May 4th will allow things to be fresh in your mind rather than waiting an entire month before you take it. But, ultimately, if you feel like you're going to take advantage of that additional month to practice and review, and you feel like you're going to do better having more time to prepare, then ultimately that's going to be your decision to make. So, but yeah, I just want to make sure that you guys know that it's important that your request, that you make that request soon so that she's able to make that change for you. Third thing is make sure that your Fulton County email address is not in your College Board account, that your College Board account is showing your personal email. So I included directions on how to change your email address, or at least to check your email address. So go in, yeah, so follow those directions and just confirm that. Last I checked, I see a lot of Fulton County email address sitting there. So you want to make sure you change it, because otherwise College Board is not going to be able to communicate with you. It's going to try to send to the Fulton County email address and it's going to block it, and you're not going to be able to get that communication from College Board. So either information about scores or information about the exam, especially if you're taking the digital exam, you need to have that open line of communication so that College Board can communicate with you. Okay, so I'll probably send out a reminder later this afternoon, just as a reminder for you to email Ms. White if you want to change the date, if you want to change your test preference, and also to change your email address in College Board. Or at least to go and check and make sure that that is not a Fulton County that's showing. Okay, any questions? Okay, we're going to finish up on the FRQ that we started yesterday. I don't think we got to part D, so let's talk about part D here. Okay, so we have temperature of water in the tub where we have specific time intervals, and we have temperature at those time intervals. It says between 20 and 25 minutes, the function W that models the water temperature has a first derivative given by W prime of T. Okay, based on that model, what is the temperature of the water at time T equals 25? So what we're going to do is we don't have W of T, we have W prime of T, which tells us how or what the rate of change of the temperature is in this time interval. So what we're going to do is we're going to use the temperature that that's last known temperature in this table, which is 71 degrees. So that at 20 minutes, the temperature is at 71 degrees, and we're going to accumulate this rate in this time interval so that we can find the change in temperature in this time interval, and then we'll take that accumulation, that change, and we'll add it to the original, to the temperature at 20 minutes, and that will get us to the temperature at 25 minutes. Okay, so basically we're going to follow this formula here, where if we're looking for a final value, it's going to be initial value plus displacement. Okay, so I'm looking for the water temperature at 25 minutes. I have a water temperature at 20 minutes, and I have a formula that will help me figure out how much has changed in that time interval. Right, so I enter this in the calculator. My W prime, I know this is going to turn into my rate of change of temperature is going to turn into the change in temperature in terms of Fahrenheit. So this will bring me up to degrees Fahrenheit. Make sure that you're in radian mode. Make sure that you're entering in X's instead of T's. And the accumulation of the rate is going to be 2.04. So we know that temperature is going to rise 2 degrees between 20 and 25 minutes. So we add that to the temperature at 20 minutes, and that's going to give us 73.043 degrees Fahrenheit. Okay, any questions with this problem here? Okay, let's go to today's worksheets. Okay, so it says let f be a function that is twice differentiable. Again, smooth curve. Table shows values of f for our selected points in the closed interval from 2 to 13. Estimate f prime of 4. So it says estimation. We can't find the exact slope at 4, but we do have some close by information that we can use to approximate that rate of change. Okay, again, squiggly line to indicate that this is just an approximation, not an exact value, or not an exact slope. Okay, so f of 5 is -2 minus 4. Change in y over change in x. Okay, no units of measure, so we leave it as -3. Part B, evaluate the definite integral from 2 to 13 of 3 minus 5 f prime of x. Show the work that leads to your answer. So you see that these are two separate terms here, separated by either plus or minus. So I think the easiest thing to do is, why don't we divide and conquer? These are not, I know we see a parentheses here, but as soon as we see a minus sign or plus sign, we can treat them like two separate problems. But they're both still going to be under the umbrella of integral, but at least we can treat these like two separate integrals and we can tackle them separately. Okay, so I'm going to treat them separately and handle them one at a time. So this side here, I can just go through power rule, right? Integral of 3. Integral of 3 is just going to be 3x. And then we evaluate our bounds, upper followed by lower. Okay, so the result of my first term is going to be 33. Second term here, I'm going to rewrite this as minus, I'm going to pull a 5 out in front. And the integral of f prime, this is really just applying first theorem, right? Okay, so first theorem says that f prime we can turn into f of x. So we know that f prime is going to turn into f of x. We can plug in our upper and lower bounds. So f of 13 minus f of 2. And then the 5 is just going to stay out in front here. So f of 13, we can pick this off from the table. So 6 minus 1. -5 times 5 is -25. So we have 33. We have the result of this being -25. So 33 minus 25 gives us 8. All right, part C. Use left Riemann sum with subintervals indicated by the table to approximate the integral from 2 to 13. So pretty straightforward. We just use left Riemann sums for our table. Okay, again, approximations. So Use squiggly equal sign here. Okay. Find the difference between each of these x values to find the width. And then we do width times height for each of the rectangles. All right. Any questions so far? A through C? Okay, part D. I want to do a little bit of an overview about this concept here before we go. Well, let me read the problem first, and then we can I can give an overview as to what this is having us do here. It says, suppose f prime of 5 equals 3, and f double prime is less than 0 for all x in the closed interval between 5 and 8. Use the line tangent of the graph of f to show that f of 7 is less than or equal to 4. Use the secant line to show that f of 7 is greater than or equal to 4/3. Okay, so let me talk a little bit about what this is, how to interpret this here. So f prime of 5 is equal to 3. That tells us that at 5, the slope of the tangent line to the graph is 3. So it's going to be a positive slope of 3. If we have a tangent line, it's going to skim the surface at a particular point with a slope of 3. Okay. F double prime is less than 0. That's indicating to us that the graph is concave down. Okay, graph is concave down. So imagine we have the concave down graph, and we have a slope of the tangent line being 3. So I want you to see the placement of this tangent line in relation to the curve. Now I'm going to move a little bit past the point of tangency here. So I'm going to pick a point C that's a little bit further away, just a little distance away from the point of tangency. Okay. And I want you to see that a point that I use to approximate using the tangent line is going to be obviously different than what is on the curve. But you see how this tangent line approximation is going to be higher than the actual point on the curve. Okay, so that's what's going to happen. If I have a graph that is concave down, any tangent line is going to sit above the curve. And because the tangent line sits above the curve, any approximation that I apply using tangent line is going to be an over approximation. Okay. And the second thing I want to point out is if I have a secant line, okay, let's say a secant line is just a line that intersects the graph at 2 points, right? Tangent line only intersects the graph at 1 point, but a secant line intersects the graph at 2 points. And if I want to approximate a point on the tangent line using, if I want to approximate a point on the secant line at C, it's going to give me this value. And if you can look at that relation there, a secant line approximation is going to be safely below the actual point on the curve. So a secant line is going to under approximate, all right, because of the shape of this graph. So if my graph is concave down, over approximation using for tangent line and under approximation for secant line. But if my graph is concave up, then that relationship is flipped around. So let's see. I want to kind of visually help you see that. We have a concave up graph. I have a tangent line through a point, and my target is, let's say, the C value is here. Notice that my tangent line now is going to under approximate a point on the curve, and the secant line is now going to over approximate a point on the curve because of the way that the curve is shaped. Okay. So there's no need to memorize this relationship. I think if you can just draw this out, you can convince yourself what that relationship is going to be, right? But I want you to at least see it so that you can, at least you have some visual anchor to base this off of. All right, so let's look at part D here. Suppose f prime of 5 equals 3. Use the line tangent to the graph at x equals 5. So let's create our tangent line first. We know the point in question is at x equals 5. So f x equals 5, our ordered pair. We got to pull this from the table. 5, negative 2. Slope, f prime of 5 equals 3. And now we can do point slope form, right? Create that tangent line equation. Okay, solve for y. Okay, so we have our tangent line equation. It says, show, using the tangent line equation, show that f of 7 is less than or equal to 4. So we want to show that a point on the curve is less than or equal to 4. So what we're going to do is we're going to plug 7 into the tangent line equation and see if there's any relationship that we can draw to help us make this conclusion. Okay, so f is talking about the curve. Here, this is my tangent line equation. So I'm going to plug 7 into the tangent line equation and see where this graph lies on this tangent line, or where the point lies on the tangent line. So 7 minus 5 is 2. 2 times 3 is 6. So 6 minus 2 is 4. So y of 7 equals 4. Okay, so y of 7 is already 4. So if y of 7, if my tangent line equation is already giving me a y value of 4, then I can guarantee that a point on the curve at 7 is going to be below 4, right? Because of this relationship that we've already established, that the tangent line is going to sit above. So if this is exactly at 4, then any point on the curve is going to be below 4. Okay, so that's the conclusion that we can make. Okay, so we'll say this. Okay, so since f of x is concave down, the tangent line will be above the curve f of x. And since our tangent line approximation is giving us a y value of 4, we know that the point on the graph must sit below it. Okay, so moving on to the secant side of things, use the secant line. So let's find our secant line equation. Okay, so basically we're now going to find an equation of this line here that's going through 2 points. It says secant line. They do give us information about the 2 points that they want us to go through. So order pair at 5 and order pair at 8. So we go to our table. 5, negative 2, and 8, 3 are the order pairs that we can use to create our secant line. Okay, so my slope, change in y over change in x. All right, there's my slope. I need to choose a point. With tangent line, you're only going to be given 1 point, so you never have to make a decision here. Here, with the secant line, you can actually choose between either of these 2 points. You can choose this one or this one to pair with the slope to do point-slope form. It really doesn't matter. It ends up giving us the same equation. I'm just going to stick with the same point that I had, but you can definitely use this point and still be okay. Okay, so there's my secant line equation. And now I'm going to solve for y. Okay, so it says use the secant line to show that f of 7 is greater than or equal to 4/3. So let's figure out what's happening at 7 for the secant line. And then we can maybe make some conclusion there. Okay, so 7 minus 5 is 2. This is going to give me 10 over 3. 2 is same thing as 6 over 3. And I get 4/3. So my secant line at 7 is sitting at 4/3. And if this point is already at 4/3, then I can guarantee that a point on the curve is going to be greater than 4/3. Right, because my secant line is going to under approximate the actual point on the curve. Okay, so this is what we can say. Since f of x is concave down, our secant line is going to sit below the curve. Therefore, since y of 7, since our secant line gives us a value of 4/3 at 7, our point on the curve has to be higher than 4/3, greater than or equal to 4/3. Okay, any questions? All right, let's go to the back page here. Okay, so Ben rides the unicycle back and forth along a straight east-west track. Twice differentiable, again, smooth curve. Function B models Ben's position on the track measured in meters from the western end of the track. Okay, measured in seconds from the start of the ride. Table above gives value for B of t and Ben's velocity. So we have a position function and we have a velocity function. So it's basically our position function here. Okay, use the data in the table to approximate Ben's acceleration at t equals 5 seconds, indicate units of measure. So acceleration we know is the derivative of velocity, but we don't have a velocity formula. Sorry, we don't have a velocity formula for us to find the derivative. So the best we can do is we can use slope to approximate our acceleration. So we know acceleration is simply the rate of change of velocity. In other words, it's just the change in velocity over change in time. So if I want to find A of 5, I can choose the closest order pairs to my source, which is 0 and 10, and I can just do change in velocity over change in time here. Again, squiggly line to indicate it's just an approximation. So I get 0.03 meters per second squared, because acceleration is meters per second per second. Right, part B. Using correct units, interpret the meaning of the definite integral of absolute value v of t. We talked about how this is referencing total distance. Okay, we're also asked to use left Riemann sum with subintervals indicated by the table. Okay, so width times height for all of our rectangles. Now I see the absolute value here, which means that if any of these were negative, we would have to convert these to be positives. But these are all positive, so there's no adjustments necessary. But it's still an approximation. Width times height. Okay, questions so far? All right, part C, between 40 and 60, must there be a time when Ben's velocity is 2 meters per second? So I think the tendency is, we want to look at the velocity and see if it ever hits 2 seconds. And, if we have a velocity below 2 and one above 2, then we can say IVT allows us to guarantee a velocity of 2 because we have a continuous function. But it doesn't cross 2, so we got to rely on something else, right? Maybe we can use the position function to help us with this. And the way position function can help is, what if we can find the slope between the two endpoints? If I can find the slope between the two endpoints, then I can come across an average velocity. If I can come across average velocity, if average velocity gives me 2 meters per second, then there must be a place where the instantaneous velocity is also 2 meters per second. And basically, we are seeing if mean value theorem can apply here or not. Right. So we're going to take our positions at the two endpoints and find the change in position over change in time to figure out the average velocity. So change in velocity, change in position over change in time. Okay, so 49 minus 9. we get 40 over 20, which reduces to be 2. So we do have an average velocity of 2 meters per second, which means that there must be an exact location where Ben is achieving exactly 2 meters per second, right? We can't have an average velocity of 2 meters per second without there actually being a specific moment in time where 2 meters per second is hit at least once. So any questions there? All right, part D. A light is directly above the western end of the track. Ben rides so that at time t, the distance L of t, which represents the distance between Ben and the light, satisfies this equation. L of t squared equals 12 squared plus B of t squared. At what rate is the distance between Ben and the light changing? So we know that the distance between Ben and the light is represented by B of t. Right, that's talking about B of t, but it's not asking about the distance, it's asking about the rate at which the distance is changing. So we know that we're looking for B prime of t, but specifically at 40. So basically, this last sentence tells us we're looking for, I'm sorry, at what rate is distance between Ben and the light, not B of t, L of t. Okay, so the distance between Ben and the light is L of t. We're asking for the rate, so we're looking for L prime of t at 40. So L prime of 40 is our ultimate goal that we're trying to, variable that we're trying to solve for part D. Okay, but let me start off with the equation. I'm going to use brackets for us to see the process a little bit more clearly. Okay, so here's our goal. We're trying to find L prime of 40. All right, to find L prime of 40, we first had to find L prime of t. To find L prime of t, we have to find the derivative, and to find the derivative, we have to involve chain rule here. Notice that there is an outside and inside portion that we have to account for. Okay, so there's an outside portion of the bracket squared. There's an inside portion of the L of t, and we're going to take turns with each of those derivatives. Okay, so bracket squared's derivative is just 2 bracket to the first power times the inside's derivative. $12 squared, that's just a constant. We know that constant will go to 0. And then B of t squared, we can go through chain rule there as well. Same setup, outside, inside. Okay, so we have our derivative equation here. We can now move towards L prime of 40, replace every t with 40. Okay. We're trying to find L prime of 40. That's our goal here. But we need to see if we have all these accounted for. So B of 40 we do have, right? We can pull this from the table, B of 40, that's just 9. Velocity, if B of t is position, then V of t is basically B prime, right? So B prime is basically my velocity function. So it's asking for B prime of 40. So B prime of 40 is same thing as V of 40, which is 2.5. So it looks like we have these values that we can pull from the table. The issue is we're missing that L of 40. Okay, there's no L of 40 that's given to us explicitly, but we do have an equation for L of t. So what if we plug 40 in here and find that L of 40 using the original equation? So we're gonna have to do a little bit more work to find out this value, because this value is not given to us directly. So okay, we'll turn to our original equation to help us find L of 40. So let's see, B of 40 we can plug in and find. B of 40 is going to be 9. Okay. And then to solve for L of 40, I can just take the square root. So I get square root of 144 plus 81, which is 225, which comes out to be 15. Okay, so we can replace 15 in for L of 40. B of 40 is just my position, which is 9. B prime of 40 is basically my velocity function, so 2.5. And now I can just isolate L prime of 40 by dividing both sides by 2 times 15. Reduce all the way. L of x, L of t is in terms of meters. So L prime is going to be rate of change, so it'll be meters per second. Okay, any questions here? All right, so hopefully you guys are able to have started on these assignments here. It's not due until next Wednesday, but if you can kind of chip away at it each day, then our assignment is 1 through 5. That is due next Wednesday, so you have a couple of days in the weekend to kind of get back on track if you're a little behind, so they can turn this in for full credit by Wednesday night. I'm going to make the assignment visible for you on Thursday, so if any of you guys are finished with the assignments, you can just go ahead and get that out of the way and turn that in. Okay. But tomorrow we'll do antiderivative word problems. We'll do differential equations Thursday, review Monday and Tuesday, review Friday and Monday, and then your test for the FRQ, just over Riemann sums and differential equations, will be on Tuesday. All right, any questions? All right, I'll send out a reminder this afternoon about Miss White's email. So if you need to let her know that you want to change to a digital exam, that you can do that promptly or as soon as possible so that she can make that change. And then also to go into your College Board account and make sure that your email is showing as personal and not as the Fulton County one. See. All right, that's all I have. Thanks, everyone. Hope you guys have a great day. I'll see you tomorrow.
Thank you.
Thank you. See you, Oscar.